Today we're talking about section 1.5, applications of quadratic equations. Okay, so what this basically means is just that these quadratic equations that we learned about, well, now we're going to see how we can use them in the real world, so to speak. Okay, so first thing, in section 1.2 we learned how to solve applied problems involving linear equations. We did this when we had Terry Bradshaw and Roger Staubach questions. In this section, we learned to solve applications that involve quadratic equations. So now we're going to be talking about equations that are now second order or second degree polynomials. We follow the same four-step strategy for solving applied problems that is discussed in 1.2. And we'll snip this whole thing and we'll do this. Okay. So this is a four-step strategy. Again, it's not something that I just follow religiously. It might be something that you might want to look at as you're starting out. But similar to you making a sandwich, right? You don't follow a rigorous step one. Okay, I gotta do this. Step two, I gotta do this. You just know. You just go and proceed through. Okay, and so I'm gonna give you and how I process things, how I go through things in my head, and maybe it might help. Of course I speak aloud and all that good stuff. So let's see. All right, so the first example we have would be to the product of a number and one more than twice the number is 36. Okay, so that is 36. Okay, so that's an easy one, right? We know that is 36. We learned basically means this, right? Is 36. All right, so and now it reads the product of a number, some number, and one more than twice the number. Okay, so if we have some number be x, okay, how do I write one more than twice the number? Well, I write, twice that number, and then plus 1, just like this. And that's my equation. Okay, and from here, well, I guess I'll expand a little bit. Okay, so let's do this. We're going to have 2x squared plus x, and then I'm going to subtract 36 from both sides. Okay. And then from here, you'll proceed with any of the number of methods that you learned. You can factor if you want to. But here, you know what? Here's my rule. Here's my own personal rule. And I can actually factor this one. And maybe my personal rule might be best for another problem, because it's a good one, all right? So anyways, if I were to factor this, I could factor this into 2x plus 9 and x minus 4. Right, is equal to 0. And then by setting z equal to 0, 2x plus 9, I set that equal to 0. I know that I've got x is equal to a negative 9/2 and x is equal to a positive 4. Now, of course, I solved this by factoring, and we know that we can solve quadratic equations in a couple of ways. Number one being factoring. Okay, if you're capable of doing it, factoring is, in my opinion, the easiest. Okay, the second way to go about it that we learned was the square root method. Okay, if we happen to have that, but let's in case we don't. The third one that we know and that works every time was the completing the square process. But we know completing the square is very tedious. Okay, so for the most part, you're probably not going to be completing the square. For fun, if I were you, if any of you going into a STEM field, maybe just if you have an extra 5 minutes somewhere, solve one of these by completing the square, because you're going to be using completing the square a lot in classes beyond college algebra. Okay, but for many of you that are in college algebra, not so much. But when we get to circles, we're going to be completing the square a lot. Okay. Anyways, let's proceed. Oh no, I'm sorry. And the last method, the catch-all method, would be to, and let's write this down. Number one, we could factor. let's write we could. We could, number one, we could factor. Number two, we could complete the square. Complete the square. And number three, we could use the, oh, that's not a U. Quadratic formula. Okay, I did say we can use square root method, but these are the main three. So we could use either of those three. And again, just quick recap. Sorry, factoring. If you can do it, do it. It's the easiest. Okay, you're probably going to skip this, but it is a way to do it. But this is going to be our catch-all, and we're going to see that. I'm pretty sure on the next one. Hopefully on the next one. What did we say our solutions was? Were -9/2 and 4. Yeah, that sounds right. Okay. Now, don't we love these? Yeah, okay. All right, so this reads, an object launched, thrown, or shot vertically into the air with an initial velocity v naught meters seconds, v naught meters per second, so m over s. All right, I said v naught. Okay, this v with that sub-zero means naught. Okay, which means the initial. So this would mean the initial velocity. This h sub-zero would be the initial height. This t, we don't have a t sub-zero. Okay, well, if we did, t sub-zero would be the initial time. So that sub-zero means the initial whatever unit we're talking about. All right, can be modeled by the equation h is equal to -4.9 t squared plus v naught t plus h naught. So here's something interesting. Okay, so I was actually having a conversation with a friend last night, and he does the whole, why do you even need this? Okay, and of course I gave him my spiel, and what's interesting, and I told him, you need to learn to do these algebraic manipulations, because when you get it to calculus and differential equations and such, you're going to be using them quite often. And this equation here is not just an equation that is pulled out of nowhere. Okay, it's an equation using differential equations, and you start off. Let's see. Well, you start off with a derivative of something, position function, and you can create these functions. Okay, so these functions that we use in this course, in the next course, those functions are created using differential equations. They're not just thrown together and slapped around until it worked. There's a very precise way to create these equations, and it's actually really interesting. Anyways, I've spent so much talking about this, or trying to chug through this one problem. The variable h is the height. Okay, so that is super duper important. The variable height, h is the height in meters of the projectile, t seconds, so t is seconds, after departure. This equation can be used to model the height of any toy rocket at any time after liftoff. Okay, so I underline h is for height and t is for time, because let's look at this example. Example 2. A toy rocket is launched at an initial velocity of 14.7 meters per second from a 49-meter tall platform. The height of the object at any time t seconds after launch is given by the equation h is equal to that. When will the rocket hit the ground? Okay, so let's write this equation out and then examine it. I don't know if I've given this little solid pro tip to you or not, but when you write your T's, at least in mathematics courses, put a little serif there at the end. I don't know if it's really a serif, but put a little tail there at the end, because I can't really tell. I mean, it's not the best example here, but notice how, I mean, my T and my plus sign, it just makes it look better. It makes it look nicer. And you know what? Just for the sake of really driving the point home, it looks the same. All right. Anyways, let's move on. So I said let's write this down and examine this equation. Okay, so we're used to x's and y's. We have t's and h's respectively, right? Because normally this might be something like x, and this might be x, something like that, and this might be a y or something, right? So we have x's and t's. Well, I underlined in red what they mean. Okay, h stands for the height, and t stands for the seconds. All right. So what is this question asking? This question is asking, when will the rocket hit the ground? When will it hit the ground? Okay, so when meaning it's asking. Okay, so what's the time, right? So when will this happen? All right, when will the rocket hit the ground? Okay, well now this is interesting. So what is the height of the ground? Well, the height of the ground is 0. Jeez. So now this is just a quadratic equation, isn't it? Okay. I mean, I can divide the entire problem by 4.9, but that might not actually stick out to you. Okay, that's oh yeah, that might not actually stick out to you to divide the entire problem by negative 4.9. Okay, the entire problem is indeed divisible by negative 4.9, and we can proceed that way into a nice, pretty equation. But let's say that you don't know, or you don't notice that 4.9 goes into 14.7 evenly. Okay, well, you could use one of we can go back to that list. We could factor it, we can complete the square, but you know what, realistically you're not going to complete the square on these, are you? So we can just skip that. You could either factor it or use a quadratic formula. Now if I were to look at this problem, here's my rule of thumb. If I cannot factor these problems in my head within 3 to 5 seconds, I go straight to the quadratic formula. Okay, so if you want to know when should I factor, when should I use the quadratic formula, there's your answer. If you can't factor it in your head within 3 seconds, move on, and that's it. Okay, but again, like I said, this entire problem can be divisible by negative 4.9, but I'll let you do that. Yeah, see, we can divide the entire thing by negative 4.9. Okay, so all right, so this reads, the length of a rectangle is 6 inches less than 4 times its width. Oh, okay then. All right, so find the dimensions of the rectangle if the area of the rectangle is 54 inches. Okay, so it's a rectangle. So real quick, let's we know that the area of a rectangle, put this over here, the area, I'm not going to put rect, whatever. The area of a rectangle, we know, is area is equal to length times width, right? That's the area of a rectangle. Okay, so let us draw a rectangle. It's saying that it's the length. Okay, so the length is the long side. Okay. All right, so this is saying the length of the rectangle is 6 inches less than 4 times the width. So what we're going to do is we're going to hark back to what we did, in section 1.2, I believe, and write this as an equation. Okay, so 6 inches less than 4 times the width. That's it. Okay. We're not told how long the width is. Okay, but that's not hard. The width is the width, right? And then the area the area inside would be 54 square inches. That is the area inside this rectangle. That is length times width. Okay, so how do I set this equation up? Well, I mean, it's pretty self-explanatory, right? All this is like this. So actually, let's do this. This is the length. This is, well, we can just put width equals width, right? And here inside will be the area is equal to 54. Okay, so now we can just kind of match it up. Well, length up here is this, so 4w minus 6. So we could say 54 is equal to 4w minus 6. That's the length, and my width is width. Okay, and I don't think anything is going to come out of this. Let's see. Okay, we'll do this. We'll go ahead and solve this a little bit. So this ends up being 4w squared. I'm just gonna put everything to the left side here, right? 4w squared minus 6w minus 54 is equal to 0. Okay, and what I did was I just put everything. I distributed here, and then just kind of put everything to the left side. Well, I kept everything on the right side, but then just kind of flipped it in my head, right? So it realistically, when I set this up, was 0 is equal to this, but I just flipped left side to right side. Okay. All right, and here's a good example. I'm looking at this problem, and I mean I know there's a relationship between 9s and 6 and 4 here, but I don't feel like dealing with it. So I just use the quadratic formula. And you may have come up with 2 solutions, but we'll have a problem like that here in a moment. Okay. Again, the hard part about these is not the algebra, right? This is the algebra that we've been doing. The hard part is setting up the equation. Oh, that's not what I want. Okay, so Jimmy bought a new 40-inch high-definition television. If the length of Jimmy's television is 8 inches longer than the width, find the width of the television. Okay, so the way we do this, and some of you may not know, and I say that because I have had students, when I say this, like, oh, I didn't know that. Okay, we have our TV here. It says Jimmy bought a new 40-inch high-definition television. Okay, so when we say 40 inches, so what do we mean by that? Well, televisions are measured diagonally. Okay, all right, so 40-inch television. If the length of Jimmy's television, so the length is going to be 8 inches longer than the width. Okay, so the width, well, we're just going to call the width W. And actually, no, we'll do this. This is a thought process problem. It's 8 inches longer than the width, so that's just W plus 8. W plus 8. Find the width. Find the width of the television. So what is the width of it? Okay, so here's the thing. Looking at this, it's not one of those simple area problems, right? I mean, we could figure out the area, but that doesn't really help us too much, right? At least, I mean, we wouldn't even be able to find the area because we don't know the area. We would be left with, W times W plus 8 is equal to the area. We don't know the area. Perimeter doesn't help us out here, so we have to think something else. Okay, so if you're looking at this, and your brain might be mush because you've done a lot of this work and you're on this part of the homework. Notice how it makes a triangle. Okay. Now, pro tip: triangles. We use well, I'm gonna say but triangles are a way to solve solutions, but they're not always going to be told to you. Okay, and I say that because I I've had calculus problems. We've had planes flying and stuff, right? But if you think about it, well, you can make a triangle out of it and then solve that way. And so triangles are really sneaky, but they're really easy. And when you figure it out and you say, oh, gotta make a triangle, you have that aha moment, and then you've progressed just a little bit in life, right? So with all that said, it's a triangle. So when we think of triangles, what should we think of? Well, we should think of a squared plus b squared is equal to c squared, right? The Pythagorean theorem. All right, well, let's plug in a squared and b squared. So the a and b are the sides of the triangle, right? And the c is the hypotenuse, okay? Well, this side of the triangle isn't highlighted, is it? No. Okay, and that's why I said we'll just stick with this. Well, that's, this is also the same width as this, right? So we can say that a, we'll just call a w squared. A will be the vertical line plus b would be the horizontal line. So this is going to be, my b value is w plus 8 quantity squared, and that's equal to 40 squared. Well, 40 squared, we're just gonna, we know that, right? 4 squared is 16, so 40 squared is 1600. Okay. Anyways, let's proceed. We can write w squared plus, all right, and then I'm going to do this thing I told you about before, where I'm not going to write out the two binomials and FOIL it. This is a perfect square binomial, so I know perfect square binomials turn into a squared, which is w squared, plus 2 times a times b, which would be plus 16w, plus b squared, 8 squared, which is 64. It's equal to 1600. Okay, well, let's combine everything. We're going to combine the w squareds on the left, so we're going to have 2w squared plus 16w plus, no, it's going to be minus 1536. And that's equal to 0. Okay, so again, I'm going to look at this. I'm going to be like, all right, so what are my factors of 1536 that when I add or subtract them together will give me 16. Well, I don't feel like going through all that, right? Or what? 15, 36, and 2. I could use a quadratic formula, and I actually will. For this problem, I will do the quadratic formula. Okay, actually, let's make it easier on ourselves, and let's divide this entire problem by 2. So w squared plus 8w minus 768. Is equal to 0. Quadratic formula time. All right, so we're going to have w is equal to, now I'm pretty sure this is factorable, okay, but for the sake of, I don't know the factors of 738 or 760 off the top of my head. I don't know if you do. So w is equal to negative b, which is 8, plus or minus the square root of b squared, which is 8 squared. So I'm just going to write 64 minus 4 that's a pretty y, huh? Minus 4. Yeah, when I try to have just a little nuanced writings, it doesn't happen. So 4 times a, which is 1, times c, which is negative 768, negative 7. Oh man, okay, so this isn't, I can't write it on here. I want to try to fit it on that page, but oh well, we're just going to live with that. Oh. Yeah, you can go away now. Okay, all over 2, hey, so all over 2 times 1. Okay, so I'm going to have to get out my calculator real quick. Okay, so when I put in my calculator, all this, and I'm using the addition sign, plus, I get W is equal to 24. Now I've got to use the minus sign, so I can just change that really easy to the minus sign, and I get negative 32. Okay, so I've got 2 solutions, right? Well, what does that mean? Well, if we were originally asked to find the width of this TV, okay, and have you ever heard somebody talk about negative width? No, of course not. So therefore my solution is W is equal to 24. It was wanting us to find, just find the width. So the width is 24 inches. So that's it. Okay, and so quadratic formula, guys. And of course, I knew it was factorable. W minus 24, W plus 32. But I mean, nobody knows that. Nobody does that in their head. Okay, so let me throw out the negative there. Speed of an airplane. Okay, so in section 1.2, we introduced applications involving uniform motion. Okay, we did the whole distance equals rate times time. We're gonna be seeing that a lot in this course. When we solve applied problems involving distance, rate, and time, we use the formula distance equals rate times time. Yeah, okay. So example 5. All right, so Kevin flew his new Cessna 02A airplane from Jonesburg to Mountain View, a distance of 2,560 miles. The average speed for the return trip was 64 miles per hour faster than the average outbound speed. If the total flying time for the round trip was 18 hours, what was the plane's average speed on the outbound trip from Jonesboro to Mountain View? Okay, so we're trying to find the average speed. Okay, so we're gonna let. Okay, let's look. We're using our formula. Distance equals rate times time. Distance equals rate times time. Okay, and r is going to be the speed, right? Because it's not the distance and it's not the time. So we're gonna denote r to be the speed, more or less. Okay, so I can't write it small. Okay, so we'll just, I don't want to write an s, but r is going to be the speed. Okay, and we are given, or what are we trying to find? If the total flying time for the round trip was 18 hours, what was the plane's average speed on the outbound trip? Okay, so what we're going to do is we're going to have to manipulate our formula a little bit. So we've got distance equals rate times time. Okay, so what if we manipulated it and instead we solved for t, right? So we would say distance over rate is equal to time. And that's okay, right? We're allowed to do that. So we're going to manipulate that equation to have time is equal to distance over rate. And then we can proceed with this. So we wanted to have the time. So let's think about this. Why did I set this up in time? So let's say if it takes me, just thinking about this, right? If it takes me 4 hours to get to Atlanta, okay? And then on the return trip, okay, so this is to there, and this is going to be from. On the return trip, the traffic was bad in Atlanta. The traffic was bad in Chattanooga. The traffic was bad. What other place? I don't know. All right, and it takes me 6 hours to get back. okay, then my total time driving was 10 hours. Okay, so hopefully that makes sense. So what we're going to do is we're going to set this problem up kind of like that, okay? So we're going to say going to, are we going to there first? Yeah, well, I mean, it's implied, okay? So going to Mountain View, okay, it's going to take us, you know, some number of hours, and we're just gonna denote it with an x for now, okay? And coming back, just put that in blue, right? And then coming back, it's going to take us some more number of hours. Y, okay? And that's equal to, well, we're told the total amount, and this is why I am solving this problem for t. And this is why I did the example of, you know, going to Chattanooga, right? My total hours is 18. Okay, does that make sense? So, like, you know, if it takes, you know, 10 hours to get there, or 10 hours to fly there, 8 hours to fly back, that's perfect. Okay, but we don't know how long it takes to get there and how long it takes to get back. That's why we rearranged this formula. Distance over rate is equal to time. So one more way to really drive this point home, and I don't know how many viewers I still have. Where can I see? Oh, well, 20. Okay, well, that's good. So we've got time 1, right? You can break it down like this. Time 1 plus time 2 is equal to, and that's going to be big T, total time. Again, the time it takes me to go to Chattanooga, the time it takes me to go back, the time it takes this fella to fly to Cessna, and the time it takes him to fly back. Time, okay? Again, that's why I solved this distance equals rate times time formula for time. So let's go ahead and fill in these blanks, okay? So in order to get there, all right, I'm going to be doing, you know, d over r. Actually, move this up. I don't like being squished. Okay, so d over, that's supposed to be lowercase d, Sherman, over r, and d over r. Again, that's just this. Okay, well, the d in both of these are the same. They're 2560. Okay, so we're going to have 2560 over some r, and 2560 over some r. Okay, all right, well, what is r? Well, let's fix this 0. All right, well, the flight there, we're not given much about r, it's just r. We flew there at some rate, that's it, okay? But the average speed for the return trip was 64 miles per hour faster than the average outbound speed. So 64 miles per hour faster would be r plus 64. And that's it. We just set up our equation. And then from here, you'll do your algebra and solve. Yeah, hopefully that was a really good, I feel like that was a really, really nice, clean explanation. Way to go, Chattanooga. And of course, you know, you work it out. You can see your video and you can see how you did. Rate of work. I think this is the last example of the section, so that's good, right? We're going to be getting out of here earlier. Let's see. I don't know if I should snip that entire thing. Yeah, this is the last example. Okay. So rate of work. We talked about rate of work in section 1.2. We introduced applications involving rates of work. Recall that when dealing with two workers that are performing a job, we use the following formula. Okay, we did 1 over, you know, the time of the first worker plus 1 over the time of the second worker, and it was 1 over their total time. Okay. rate of work. The rate of work is the number of jobs that can be completed in a given unit of time. If one job can be completed in t units of time, then the rate of work given is 1 over t. Okay, so let's look at this. Dawn. So let's do this. Let's do a thought process. Okay, we're gonna have. It looks like we're gonna have a dawn, and we're gonna have an atom. Okay. So Dawn can finish the monthly sales reports 2 hours less than it takes Adam. Okay, that's not hard. So if Adam does it in t time, then Dawn does it in t minus 2 time. And that's it, right? And that's all we need. And the total time is 8 hours. Yeah. So if we were to follow along with this and what we did in section 1.2, what we would say, Dawn's time, so 1 over t minus 2, plus Adam's time, which is 1 over t, is equal to total time, which is 1 over 8. And that's it. We just set up our problem. Okay. And again, the algebra is something for you to work out. And that concludes this lecture.